Hello everyone, welcome to this IROS2020 presentation. My name is Qingru Li, and today I'm going to talk about our method of generating probabilistic semantic map for urban autonomous driving applications. In this talk, I will first show you guys the motivation that drives us to tackle this problem and the related work in the literature. We will then dive into the details of our method and talk about three important components of our system. In the next step, we will illustrate the experiment setup and present the result that we use to verify the design of our method. In the end, I will conclude this talk with a brief summary and a discussion to the future work. The motivation that drives us to tackle this problem comes from our observation that today's autonomous vehicle often relied on high-definition maps. High-definition maps, also known as HD maps, offer centimeter-level road information such as stop lines, crosswalk, and the landmarks for the vehicle to drive safely in the road. One important information that it contains is the semantic meaning of objects in the scene. Here we show a road network image that we use for our self-driving car at UCSD campus. With the help of the red circle stop line and the planning trajectory highlighted in both blue and gray, our vehicle is able to drive automatically around the campus and deliver mails to each college without breaking any traffic rules. Even though these semantic labels are beneficial to the downstream tasks like planning and navigation, creating them is actually very expensive and time-consuming. Small regions like this usually take us a day to generate. Imagine the second day after you finish labeling the map, you drive the vehicle on the road and encounter this situation. The campus is now under construction. The entire road is blocked by traffic poles, walkers, and the construction vehicles. The map that you generated yesterday is now already outdated. It would be very painful to recollect the data again and do the labeling. The dynamic change of the environment motivates us to think if we can automate this HD map generation process, starting from extracting the semantic information on the road. We want to reduce the label work and help vehicles to handle dynamic driving environment better. In the literature, existing approaches for the outdoor semantic map generation includes using planar assumption to create a 2D bird's eye view map, or use a 64-channel LiDAR point cloud to build a 2.5D semantic map, or using the stereo camera to do the depth estimation and reconstruct a semantic map in the 3D space. None of them have solved the problem perfectly. The planar assumption will create distortion on faraway objects. The 64-channel LiDAR is very expensive in the market, and the depth estimation for a stereo camera meets the accuracy that an HD map requires. And not to mention that neither of them capture objects like landmarks and crosswalk, which indicate some critical traffic rules. Therefore, in our work here, we are interested in using low-cost LiDAR to collect accurate depth information and avoid planar distortion. We also want to leverage the visual cue from cameras to capture objects in the scene that conveys important traffic information. Here we present an overview of our pipeline. Our autonomous vehicle first collects the camera image and the vehicle pose while it is driving along the campus. It uses deep learning neural network to do semantic segmentation on the RGB image and then extract a small region of the point cloud centered around the vehicle. We associate this local point cloud with the semantic label in the image, which can give us a semantic point cloud. And once we have it, we project those points into a bird's eye view semantic occupancy grid and use a probabilistic model to handle the uncertainty of the environment and make our map less sensitive to noise. For the image semantic segmentation task, we implement a deep lab v3+ network and train it on the mapillary dataset. The backbone of the network architecture is a ResNext 50 pre-trained on the ImageNet. For the dataset, the original mapillary data offers 66 labels, and we remove the labels that are not likely to appear in our environment, such as snow and tunnel, and merge labels that have similar meaning together. In the end, we have 19 classes in our training dataset. A detailed list of our training labels is shown in the first table of our paper. Once we have the semantic image, we use the vehicle's pose to localize itself in the dense point cloud map. We then take a small region of the point cloud centered around the vehicle. By using the camera's intrinsic matrix and the translation matrix between the LiDAR and the camera, we can project this local point map into the semantic image that we generate and find the associated semantic labels for each point in the point cloud. Once we have the semantic point cloud, we project them into a bird's eye view semantic occupancy grid. The semantic occupancy grid uses a probabilistic framework to update the semantic distribution on each cell. The update rule for each cell at time t is shown in the equation on top of this slide. Here we are using the observed semantic label z, LiDAR intensity I, and our previous estimation on the map to evaluate the semantic distribution S on every cell of the grid. By using the Markov assumption, we can update this probability recursively. The key components of this formula are to model the probability of the observed semantic label Z and the LiDAR intensity I conditioned on the semantic distribution S. We use the confusion matrix from the semantic segmentation network to model the probability of Z conditioned on S. The confusion matrix that we use is shown in Table 1. The network is very confident in predicting road and vegetation. But in terms of the crosswalk and the landmarks, the network is more likely to make mistakes, tending to predict them as road. By taking this behavior into consideration, we can weight our estimation across different classes, and finally generate a semantic map that can capture all the road features in the scene. Regarding the probability of observed LiDAR intensity I conditioned on S, we determine a heuristic function to assign a higher likelihood to the cell when the observed labels are crosswalks and landmarks. An example of our generated semantic map is shown in Figure 1. The experimental setup that we use to validate the performance of our model is the self-driving car platform on the UCSD campus. As shown on the right-hand side of the image, we have a 16-channel well-done LiDAR running at 10 Hz for pose estimation and dense point cloud generation. We also have two forward-facing cameras running at 12 Hz for semantic segmentation. We select a 1.1 km road trajectory to test our model and create a semantic annotation from a top-down view. The Figure 1 shows two segments of our ground truth labels. The purple represents the road, the white represents the landmarks, and the brown represents the crosswalk. The label is defined with respect to the dense point cloud map with a 5 cm level accuracy. Figure 2 is a bird's eye view dense point cloud that is thresholded with a certain LiDAR intensity. The white points are point clouds that has high intensity. As we can see here, the crosswalk and landmarks on the image are highly visible. We leverage this information to help us identify the road conditions during the data labeling. The evaluation matrix we use here is intersection over union and the pixel accuracy. Our vanilla model uses a uniform distribution to model the probability of the observed semantic label conditioned on the semantic distribution. In contrast, CFM model uses a confusion matrix to model this probability. The plus I here indicates the augmentation of LiDAR intensity on the landmark prediction. The result of the IOU and the pixel accuracy is shown in Table 1. As we can see here, even though the vanilla model has a slightly better estimation on the row, its performance on crosswalk and landmarks is way lower than the CFM model. We observe a 6% improvement in terms of the mean of the IOU when switching from the vanilla version to the CFM version. When augmented with the LiDAR intensity, we observe a noticeable improvement in the class of landmark at the vanilla version, while the prediction on road and crosswalk is preserved. However, we do not observe similar improvement on the CFM plus I version, which showcased the simplicity of using confusion matrix to generate a more robust estimation. We also study alternative methods for the semantic association. Examples of the semantic map generated by using planar assumption and the sparse LiDAR point cloud are shown in Figure 2 and 3 respectively. In this image, the blue box indicates the location of the ego vehicle. The planar assumption will cause distortion on far-away objects, and the direct use of the 16-channel LiDAR cannot provide sufficient data for us to model the environment. In our method, even though we need to create a dense point cloud map beforehand, the data is collected only once, and with the second run, we can get the semantic map automatically. After this, the map that we generated does not have the disadvantage as shown in the two alternative examples above. Here we make a side-by-side comparison between the labeled ground truth and the semantic map generated by our model, showcasing the fidelity of our map. A region has also been scaled up in our map to show the details that it encapsulates. It demonstrates our model's capability to generate a large-scale map accurately and automatically, paving the way to generate HD map that is important for the autonomous vehicle applications. To summarize, we leverage the image semantic segmentation and the LiDAR point cloud to generate a semantic bird's eye view map. Our statistical approach, formulated with confusion matrix and the LiDAR intensity, effectively localize the row features, which is essential for the HD map. Even though the real-time performance has not been realized in our model, being able to generate such a semantic map without human annotation is still very attractive for a robot that runs in a dynamic changing environment. In terms of the future work, such a dynamic mapping algorithm has the potential across different areas in the autonomous vehicle application. For example, we can use it for dynamic planning and path tracking algorithms without dependence on HD maps. This map representation can also be used for trajectory prediction or road users' intent recognition. It is also helpful for scene understanding or automatic generation of the road network for HD maps. That is the end of my presentation. Thank you for your listening. If you have any questions or comments, please let us know. You can reach out either of us from the email below. We are looking forward to hearing from you. Thank you for your time, and I wish you have a wonderful day.